Here we see a charge Q1, 5 microcoulombs, and a charge Q2 of negative 2 microcoulombs. First charge lies at the point 0, 0. The second charge at the point 1, 0. We want to find the electric field due to these two charges at the point A, 0.5, negative 0.5. This point lies halfway between the charges, well, at equal distances from the charges, on the perpendicular bisector of the line segment connecting the charges. We first determine, well, we're not going to actually determine the electric field, we're just going to do an estimate. Okay, we estimate that the field E1 is going to be greater than the strength of the field E2. E1 is the force, or the electric field due to the charge Q1. E2 would be the electric field due to the charge Q2, provided that each of these charges was, that each of the charges Q1 and Q2 was there independently. That is, E1 is the field that we would have if Q1 was the only charge. E2 is the field we would have if Q2 was the only charge. Now, to estimate the relative strength of E1 and E2, we note that since we're at the same distance, the proportion of the field strengths will simply be the proportion of the magnitudes of the charges. So that since Q2 has magnitude 5 microcoulombs, Q1 has magnitude 5 microcoulombs, Q2 has magnitude 2 microcoulombs, the electric field due to Q1 will be 5/2 as great as that due to Q2, so that these vectors are in approximate proportion 5 to 2. The other thing we note is that since Q1 is a positive charge, E1 will be away from Q1. And since Q2 is a negative charge, E2 will be toward Q2. So that we estimate that the electric fields will look something like this. And that the resultant field vector, of course, will be obtained by drawing a parallelogram and using the diagonal across a parallelogram as the electric field vector, the resultant of E1 and E2. Now, comparing what happens at point A with what happens at point B. We come over to point B and we're much further away from the charge Q1. We're actually a little bit closer to the charge Q2. Okay, now being somewhat closer to the charge Q2, the electric field E2 that's directed toward Q2 will be a little bit greater than it was over here. The electric field E1 due to charge Q1 will be much less than it was here. We're almost twice as far away from, matter of fact, we probably are twice as far away from Q1 as we were at this point. Now, if we're twice as far away due to the inverse square nature of the force, E1 here would have only 1/4 the strength that it has here, because at twice the distance, R squared would be 1/4 as great. Same charge, 1/4, well, a factor of 1/4 gives us an electric field that's 1/4 as great. So that we have these two approximate vectors with this approximate resultant. But we can see as we move further and further away, in the first place, if we move out in this direction beyond point B, that is, we look at point A, then point B, and move beyond point B, the electric field due to each charge is going to fall off rather rapidly as we move away. Now, if we move over here on the other side, starting at B and then A and moving beyond A in this direction, we're going to come closer to the 5 microcoulomb charge, so that the strength of the electric field due to the 5 microcoulomb charge is going to increase, while that due to the negative 2 microcoulomb charge here is going to decrease. So what we want to do is we want to actually examine what happens as we move along this y equals -5 line. Now here's the point that we originally called A, and here's the point B. Here are the field vectors at A and at B. The question is, what do the field vectors look like at all these other points marked by red dots. So you should really try to do that. You should try to figure that out, make your own estimates of how the field vectors will change before we go on to the next clip and we show you exactly what's going on.